Hello, today we will discuss orders of the numbers. And what is order? If we are given any prime number p and positive integer a, and if we know that order of a mod p equals k, this means that k is the first number. There, if we take a into the k power, this number must be 1 mod p. And the most important feature of the order is that if we are given that a to the m equals 1 mod p, then m must be divisible by k. To prove this, let's represent m as k times q plus r. The r must be the remainder by division by k. So r must be less than k, less or equal to 0. So a to the m must be equal a to the kq plus r. So this equals a to the kq times ar, a to the r. Because we know that a to the k equals 1, this equals 1 to the q times a to the r. And if we know that this equals 1 mod p, we have found less number than k, r in our case. The a to the r equals 1 mod p, and this is the contradiction of the order statement, because k must be the least positive integer. There, if we take a to the k power, this will give us 1 mod p. So this is contradiction, and r must be 0. Contradiction, and we get the r must be 0, so m is divisible by k. Next, a very important feature, characteristic, is that if we are given two numbers, that a to the m equals a to the n and equals 1 mod p, then we can see that a to the GCD of m and n must be also 1 mod p. To prove this, we need to use Euclid's extension algorithm, which we have discussed in the previous videos, and also inverse reminders, because we know that a to the m equals 1 mod p. We can see that a to the mk equals 1 mod p. Also, we can see that a to the negative mk must be 1 mod p, because this must be the inverse of the previous number, and inverse of 1 is itself 1. So it has no matter, it will be positive power or negative power, which is multiple of m. This will give us 1 mod p. And in the previous video, Euclid's extension algorithm, we have discussed that we can always find a, not a, in our case it was c and d, such that c times m plus d times n must be 1. Not in modulo. This number must be 1, and any of them may be non-negative, and maybe one of them negative numbers. So in this case, we can conclude that if we take a to the n to power of d, then and get a to the m power of c, and take their product, this number must be a to the this must be GCD, sorry. In our case, if m and n are coprime numbers, this must be 1, and if they have some GCD, this must be GCD of m and n. And a to the n power d and a to the m power c, this number must be GCD of m and n. But we know that this is 1 mod p, and this is also 1 mod p. So we have proved that a to the GCD of m and n must be also 1 mod p. Also, if we look at the Fermat's little theorem, we can also see that p minus 1 is always divisible by the order of any prime number, or p, a. And we can also always see that order must be a divisor of p minus 1. Otherwise, Fermat's little theorem will not be correct. So this was all I wanted to discuss for today. If you got any theorems to discuss, please write in the comments.